Alright, so now we're going to look at a problem that we had previously seen, but we're using a different method. The statement reads, we determine the electric field outside a spherical conductor, radius r, placed in a uniform external field E naught. Solve the problem now using the method of images and check that your answer agrees with the result. Alright, so let's take a look at the diagram. Here we see the spherical conductor in the middle, with charges plus Q and minus Q at a distance A from the center. These charges are what produce the external field, and we wish to place two image charges on the inside, a distance B from the center, a plus charge and a minus charge. Okay, and we see that the separation distances are script R1, 2, 3, and 4, and our field point is some point away from the origin R at a given angle theta. So now we can form the potential for the situation. Recall that for a point charge, the potential is just Q over the separation vector R. So for our 4 point charges, 2 primed and 2 unprimed, we see that we have Q over R1, R2, and Q prime over R3, R4, factored out, but do note that there's a minus sign in between the parentheses for the negative charge. Now that we have this form set up, we need to determine what these separation vectors are, which are just separation distances in this geometry. Here we can see that by the use of law of cosines, we find this pretty easy. Note that for the unprimed coordinates, we have a distance A with a plus or minus due to the origin. And then for the prime coordinates, we have a distance B plus or minus from the origin. Now, if you recall, we used a binomial expansion in the text to find out what these inverse relations approximate to when A is much, much greater than R. Here we see the approximation in blue is just 2R over A squared for cosine theta. Note that as A gets much, much bigger than R, that goes to 0. Now expanding for where B is much, much less than R, since the image charges are on the inside of the conducting sphere, we see that we get a similar situation except for the numerator has B in it and the denominator has R in it to make sure it converges. Also note that from the geometry, B is equal to R squared over A, which was found or established in the previous problem, so we substitute that in and we get the result in purple. Also note that the image charge had the ratio of negative R over A, Q, which was also determined in the previous problem. All that just to substitute into the potential formulation that we had last time. Once we do that, then we see that we have a common factor amongst the blue, red, and purple, and we can factor that out. That factor is 2Q over A squared. We also note that both those terms have a cosine in it, and we post-factor that out, leaving the terms in the bracket as just a couple of R's. The problem stated that the spherical conductor was placed in a uniform external field, E naught, which is produced by the point charges on the outside of the sphere. We know what the electric field of a point charge is. It's 1 over 4 pi epsilon naught Q over R squared. We have 2 point charges, add them together. In this case, the R is just A. We push that minus sign over to E naught so we can substitute into what we found in the potential. And thus we can see that our potential that we found using the method of images is the exact same as what we found previously.